So hopefully you guys online have done what we have done here, which is go through Levi's lecture, a little bit of the sound glitch in the beginning of it that he corrected after a bit, but hopefully the rest of it was, at least the language was pretty understandable. I don't know about the material, but the language was interpretable. This is kind of a complicated regression, linear regression, nonlinear regression, multiple regression, logistic regression. They're really pretty advanced topics as far as statistics are concerned. Mainly in this course, we're going to be looking at simple linear regression, where we're looking for a relationship between two numerical variables. We threw out a bunch of them before here in the class. One of them that we threw out was something like blood pressure and a person's age. As a person gets older, maybe their blood pressure gets higher and so on. Or BMI and blood pressure, two numerical variables that presumably have some relationship to them. Okay. When we talk about correlation, we're just looking for some association between them. We're not predicting that one of them is the cause of the other. Okay, so for instance, in BMI and blood pressure, you might be able to argue that BMI has some influence on a person's blood pressure. Okay, on the other hand, unless we have clinical evidence of that, and some other way to demonstrate that that's likely to be true, we may want to just start out with just looking for the association that, for instance, that as BMI goes up, blood pressure goes up. Not worry about which one is causing the other to increase, but just look to see if that really is true to start off with. Okay, and that's what we talked about last week. That's just simple correlation. I'm going to open up a data file, and we're going to give that a try for starters. Okay, and this particular data file has temperatures and heart rates for a number of subjects. Both of those are numerical variables, right? Heart rate is a numerical variable, beats per minute, and person's temperature in degrees Fahrenheit is a numerical variable. See how many subjects that we have here. We have 130 subjects, and we've measured, we've randomly sampled 130 people from the population, and in that population we measured the person's temperature, happens to be in centigrade, as it happens, rather than Fahrenheit. Okay, we measured their temperature and we measured their heart rates. Okay, we're curious to see if there's a relationship between these two. No causation yet. We're just looking at whether or not there's a relationship. A correlation, at least is there one thing in statistics where the word pretty much means the way we use it in English. It's correlation. We're looking for that, just that association. So let's go ahead and do that. We're going to say analyze, but before we do that, maybe there's a simpler way we can look for a relationship. So for instance, we know graphically, we can see a lot of things about large sets of data that are hidden from us if we just stare at the numbers. So I'm going to go into graphs. I tend to use legacy dialogues. You could use Chart Builder or one of the others. Doesn't matter. I'm going to go into scatter dot. When I choose scatter dot, okay, it allows me now to create an XY axis where the x-axis I can define as one of these variables and the y-axis I can define as the other variable. For correlation, it doesn't matter which one I choose. It's going to work out the same way no matter whichever one I choose. When we get into regression, we're looking at trying to predict which one causes the other. Does blood pressure cause temperature to go up, or does temperature cause blood pressure to go up? When we're looking at causation, where one of them is a variable that is dependent on the other, independent and dependent variable, or from another sense, you could call it a predictor variable and a response variable. In other words, person's temperature goes up, their heart rate goes up also. The predictor variable is their body temperature. The response variable or dependent variable is their heart rate. So that may be true, maybe it's not true. But for our purposes right now, we're not interested in that. We're just interested in taking a look at this at a simple scatter plot. Now, what we're going to do at a scatter plot is each one of these values, for instance, this subject number 5, we're going to plot on an XY axis, we're going to plot their body temperature and their heart rate. The x-axis is going to be their body temperature, and the y-axis is going to be their heart rate. So those two numbers are a point on an XY axis. Wherever the value is, X is this and Y is this, that's where it's going to be located. And we're going to plot every one of these points at the same time. Click OK. And let's take a look at this correlation. Okay, let's take a look. Does it look like there is an association there? Sure doesn't look like a very strong one, does it? Okay, I'm going to double click on this. I'm going to ask SPSS to give me a best fit line here. And this line best fits the data in a manner where, oops, went away. I think if I close that, it should transfer there. Okay, this line gives me a line. Let's see, maybe not. Let me undo that. No, it won't let me undo that. I'll choose the right one. Oh, no, I think I got the right one. No, I didn't get an R square though. Why did I make an R square? Scatterplot, let's see. Let me try this again. Graphs, legacy diagram, scatter dot. Okay. Rescale it. I don't think I have all my options here. There we go. That's it. There's our best fit line right there. What does that mean, best fit line? What we're doing there is what SPSS is doing for us is it's taking all of these points and it's taking the errors from that line, the distance from that line for each one of these points. For instance, this particular person that's represented by this dot right there, they have a, see if I can hover and get the value for that. They have a, not given to me, let's see. Their heart rate is about, looks like about 83, and their body temperature is about 37.2 degrees centigrade. Okay, and if I picked another dot, it would be different, and so on and so forth. Well, this line is intended to predict what a best fit, what a person's heart rate would be based on what their body temperature would be. So the ones that fall, the dots that fall on this line are almost perfectly predicted by this line, the formula that represents this line. All the ones that are above it and below it, that distance that they are from this line is the amount of error between the actual value and what that line would predict that their heart rate is based on their body temperature. So what SPSS has done is balance these, take the square of all these, take all these differences, square them, and balance them between the those above the line and those below the line. Right? So it minimizes the total errors that are generated, total sum of errors here, total differences. Now some of these are way off. For instance, this person right here is likely to be an outlier. Right? They're much different than all the other values. I'm not going to worry about this for correlation right now. When we talk about regression, outliers are a problem, particularly when they're at the far end of the range that we're looking at for our predictor variable, right? Because let's say you have a value that's an outlier up here. You can almost look at this as a, you guys know what a teeter-totter is? Kids get on, like the two kids get one, yeah, seesaw. There you go, seesaw. So if you have a value that's in the middle, right? It's going to tell, and it's high. For instance, it's in the middle of the predictor axis, but it's a high value. It's going to tend to pull that line up, but not change its slope very much, right? But if you have one that's at the far end or the low end of this range for the x-axis, it's going to tend to drastically affect the slope of that line. Slope of that line is particularly important to us because the slope of that line tells us the relationship between heart rate and body temperature. In other words, the slope tells us that if we increase 10 beats per minute in heart rate, how much that affects body temperature, or vice versa. So that's really the slope that really gives us the relationship here, right? So you need more than the slope to draw the line, but you also need a y-intercept. You also need a point at which that line crosses the y-axis so that you can anchor that line and predict what its actual path is, right? I have a real graph then. Okay, so that's our correlation. So now I'm going to take this and I'm going to try and quantify this now. And I'm going to quantify it by calculating the Pearson's correlation coefficient. And basically that's a rate that shows you the relationship between the amount of variability that there is in these errors and the overall variability in the values that we're seeing. So let's calculate that, SPSS. And I think I need to get out of this to do it. Here we go. I'm going to analyze. I'm going to go to correlate, bivariate, because at this point we're still only working with two variables. Again, both numerical variables. I'm going to move both of these numerical variables. Doesn't matter which one I put on top or the bottom, because we're still at the stage where we're just talking about looking for an association. I'm going to click OK. So now this gives us a measure of what the association is between these two variables. This R value that we're talking about, the R value can range from -1 to +1. If we have a perfect correlation, every one of the values lines up, every one of these people's heart rates and blood and body temperatures winds up perfectly on a straight line that we've predicted based on this. If everyone winds up perfectly on that line, that's a perfect correlation that would have a correlation of either 1 or -1. If it slopes upwards, like this particular one does, it's a positive one. Slopes downwards, it's a negative correlation. That's one value. As the x-axis goes up, the y value goes down. That's a negative correlation. Okay, so let's see what we have. We have a Pearson's correlation of 0.234. Well, a strong correlation would be 1 or -1, right? 0 would be no correlation at all, no association, just random values for body temperature and the heart rate. Right, so we do have some correlation. It's not a very strong one, but we do have some correlation. Now, if I look down here, the significance, the probability, the p-value is 0.004. Well, what is that telling us? That's telling us that even though this may not be a terribly significant or useful association because it's only 0.25, it is telling us that it's a statistically significant result. In other words, if our null hypothesis is that there's no association between body temperature and heart rate, that would be an R value equals 1. So you could use either one of those as your null hypothesis, right? One, you could say there's no association between body temperature and blood and heart rate, or you could just say that the R value for those two variables is equal to 0. That's your null hypothesis. Well, in this case, yeah, you'd be rejecting that and saying that there is an association. Clinically, is it as important an association? Is it a good measure? Well, that remains to be seen, right? It doesn't look like it's that good an association so far, but statistically, you'd be right in rejecting the null hypothesis because it's not, there is some association. It's not 0 association. Okay, so that's what we know about this at this stage, right? So now, which do you guys think would be a predictive variable here? I'm thinking that body temperature would predict heart rate, right? In other words, if you have a temperature, you have a cold, you have heart, you typically have a higher heart. Am I wrong about this? You guys more clinicians out there than me, right? I'm not sure about this, right? I think that's right. I'm gonna go with that assumption since nobody here is contradicting me. Right, let me see if anybody online said anything. Okay, somebody capitalized, yes, we can hear you. Good, glad to hear it. I guess they can really, I guess it must be loud. Yeah, exactly. Okay, so let's take a look at this from another perspective. where we're actually going to try and use one value to predict the other. So I'm going to go here, and this is what we worked on. This is a kind of review of last week. We're going to go to Analyze, and we're going to go here to Regression. Anybody here like read the textbook and see any mention of where that term regression came from? No? Nobody? Okay. Doesn't sound like it doesn't sound to have much, it doesn't sound like it has much to do with what we're doing, this idea of regression. Yeah, and the regression is based on the statistician that developed this analysis method was working on, I think he was working on analyzing the heights of offspring of people, that short people and tall people. And what he found was that when you had started with two tall parents or two very short parents, that typically it's more likely that the offspring would be not as tall or not as short as either one of them. In other words, the offspring regresses towards the mean of the population, which you'd say to yourself, well, gee, a tall person can be a tall kid, right? But then you say, well, they're both tall already. So, you know, the chances are that kid's going to, nutrition being the same, you know, that kid is going to, you know, probably be more like the rest of the population rather than be exactly the same height because his parents are already kind of outliers, right? So that's regression to the mean is what that was based on. And this is where he developed this technique, right? So this regression really doesn't, the word doesn't really describe too much of what we're doing. So I'm going to say linear regression, which means that we're looking for a linear relationship. Not all relationships are linear. Some of them are exponential. Some of them are logarithmic, right? So you can't apply this to everything. The assumption here is that this particular relationship you're applying it to is a linear relationship. Okay, so let's take a look at this. The independent variable. Now at this stage, instead of just moving them back into there like I did for correlation, in this case, I'm going to move my independent or predictor variable into the x-axis, which is down here. So that is going to be my body temperature. And I'm going to move my heart rate, which was my dependent variable or response variable, which is predicted by the body temperature, into the dependence. So anyway, let's take a look at what we have. I'm just going to go ahead right now and go ahead and run this analysis and see what it gives me. Okay, so let's see what we get. First thing it tells us is that that we entered the variables that we entered was body temperature. Let's see, and so our R value, our Pearson's R value, the correlation, is equal to 0.254. Okay, and that is our same value that we got when we ran the correlation previously. Now R squared, we discussed R squared in the lecture. R squared is based on this correlation value and some other ways of measuring it as well. R squared gives us an approximate way of understanding how much one variable impacts the change in the variability in the other. So like in other words, if we increase if a person's body temperature goes up, how much does that predict how much of a change you get in his heart rate, right? Well, it tells us that based on R squared, that it only predicts about 6% of the variability of, say if each one of these people that were in this study, their body temperature went up not 10 degrees, they'd be dead, right? If it went up 10 degrees. If it went up like 4 degrees or something like that, what their resulting heart rate might be. Only 6% of the variability in those heart rates is predicted by this analysis. That's not very good, right? That means that 94% of the variability is other stuff that's predicting it. Could be physical capacity, it could be exercise, it could be BMI, it could be general health, it could be age, and so on and so forth. But there's many other factors that are probably more important than this. So even though we got a statistically significant result for our correlation, and we also got a statistically significant result for our regression, which tells us that there is an association and we can create a formula to try and predict it. It's just not going to be a very good predictor. Now you'll notice that there's also an adjusted R square. There's several, I don't think we went over it too much in detail in the lecture. There are several assumptions for regression. You can catch up on this in the textbook, I think. Several assumptions for regression. One of them is that these variables that we're using are roughly normally distributed. If they're not, if they're skewed and they're not normally distributed, that can throw a monkey wrench into this to some degree, right? Doesn't have to be perfect, but it can throw a monkey wrench into it. The other thing is that it's important, think about this. If we're trying to demonstrate a relationship between body temperature and heart rate, we want each one of them to be spread out over a larger scale. If we only have people whose body temperature is between 98 and 99 degrees, that's not going to tell us very much about how good a predictor this is, right? So we want large sample sizes if we can have it. Typically, we want at least 15 people, 15 subjects per variable that you're going to analyze. So here, we'd want at least 30 subjects, right? And we wouldn't want the subjects to be all grouped in one area of temperature or heart rate. We want them spread out. The other thing is that if your variables for temperature go from 97 degrees to 102 degrees, right? Usually that's all you have data for. Usually you have to be very careful about expanding your predictions on values that are outside of the range of values that you were working with, right? So you have a bunch of things: normality, how normal these things, how many variables you're analyzing in this case, and simple linear regression only 2. Well, we're going to go further than that, and the normality, the number of variables, and the sample size. So in order to adjust for issues that we might have with sample size, the number of variables that we're using, normality issues, and also, as we go into multiple regression, the number of variables that we might be using and the level of collinearity. We're going to talk about that later, but the level of how each one of them, the particular variables that we're going to use in multiple linear regression, how collinear they are, how much of a correlation between each one of them that there is. Those are all going to impact this R-square value, so that they're not going to impact this. They're all going to negatively impact this R-square value. Too small a sample size, too many variables, collinearity, going to negatively impact this. So it overestimates how predictive this analysis is. So in a lot of studies where they're concerned about sample size or number of variables or collinearity, they'll report the adjusted R-square instead of the normal R-square. Okay, so if you see it in there, they're being more conservative, basically, when they report that 0.057 versus the 0.064. Okay, still a statistically significant result. This formula really represents an association between these two variables. So let's take a look at that. We get a coefficients table. The coefficients table gives us what we need in order to write this formula, create this formula. Okay, let me get to that. Okay, let me open a new one. Let's see what these values are that we got. Okay, so typically with a simple linear regression, the formula that we would create is that y, the dependent variable, is equal to a plus bx, where b represents the slope of the line based on the value and the value of x, whatever the value of x. In this case, we're going to say that y is the heart rate, is equal to that value a. This value a is a constant. That's the y-intercept, plus b is the slope. Yes, could also be a negative, right? Times the value of the heart rate body temperature. Okay, times body temperature. Slope times the body temperature. If it's a negative, what does that tell you about the line? Slopes downward. Negative slopes downward, right? Negative association slopes downward, right? Because as x gets bigger, As you're further out on the x-axis, the y value goes down. Right? Okay, so the slope is, if it's negative, that gives you a negative correlation. If it's positive, it gives you a minus slope upward. Actually, think about that. Oh, no, I'm glad you brought that up. She's holding, for you guys that are not here, she's holding her arm straight flat, so parallel. What's the R value for that line that's parallel? Guess again. Bingo, 0, right? Think about it, because the x-axis has nothing to do with what the y. If the x-axis is, what's that? No association whatsoever, because if the body temperature is 30 degrees or 35 degrees or 40 degrees, no matter what it is, you have the same y value. So it has no effect on it. So it's no correlation. So yeah, it's interesting, right? So just that one thing. Okay, in fact, most of the time, the way you would see a scatter plot where you fail to show a correlation is you'd see basically kind of almost like a square random plotted of dots, and then like if you drew the line, it would be just go straight through it, right? In other words, the balance of it would just be a straight line, right? So that would be kind of what situation you would have. We don't have that. We have a slightly upward slope, right? So a lot of scatter, not a great predictor, but a lot of scatter. But at any rate, so now this is what our formula is. Now, if we go to this table, right, let's interpret this table. This table tells us, let me bring this up a little bit. This table tells us that the y-intercept is -88, and the body temperature slope for the body temperature is 0.4398. I'm going to call that 4.4. Okay, so substituting those, the heart rate, which is our response variable or dependent variable, is equal to -88 plus the slope of 4.4. Oops, why is this not cooperating? Times the body temperature. Right, so we have a formula that we can use to predict heart rate based on body temperature. Okay, so 4.4, what does that tell us? For every degree centigrade that we go up in body temperature, the heart rate goes up 4.4 beats per minute, right? So we're using this slope to give us an idea of what this relationship really is. This -88, it doesn't really have much meaning, does it? But we need it, because if we don't have it, we can't draw the line. So now when we drew this scatter plot, let me go back to it. When we drew the scatter plot, notice the x-axis. The x-axis goes, oh, you know, I did it the other way around. Let me do it again. Graphs, legacy dialogues, scatter dot. And I'm going to go in here. And this time I'm going to move these around. I'm going to put them in the order that it would have been if I thought about the, which one was causal, which one's body temperature is going to be in the x-axis, or it's going to be in y-axis. Okay. And okay, there we go. And there's the formula, by the way. Notice that formula is there as well. Okay, see, there's our formula, negative 88.1 plus 4.4 times x. Now, you'll notice that the y-axis goes from 35.5 to 38.5, right? That's normal temperatures for human beings, right? So it doesn't go through the, what would the y-axis be down? What would the value for x be at the y-axis? It'd be 0. 0 is all the way over here off the screen or to the left. It doesn't exist on this plot at all. But we still need 0 in order to, we know the slope is like, the line has this slope, but we don't know where it goes on this chart unless we have at least one point to pin it to. And that point that we can pin it to is the y-axis. So if I were to draw this, chart out completely, right? The area that we're looking at is over here. right? The actual, if I extend this, the place where it crosses the y-axis is negative 88, right? Which really doesn't mean anything to us because we're only concerned about this area here. We're not attempting to make any other prediction, but we need that point so we know how to draw this line. We need at least one point. In other words, the intercept. Okay, so now we have a formula for this. Now, if we want, we can now go back and we can test this formula to see how good a predictor it is for the sample people the subjects that we have in our sample. So I'm going to go here, and I'm going to go to Analyze. I'm going to go to Regression Linear, and I'm going to click into this box that says Save, and I'm going to ask it to give me the unstandardized predicted values and the unstandardized residuals. And I'm also going to ask it to give me these as well. Okay, I'm not going to worry about them anyway. At the moment, I'm going to ask it to give me those as well. Okay, so what happened here? It doesn't look like much changed over here. However, if I go back to my output, if I go back to my data file, you'll notice that there's two new variables, actually more than two new variables. There's our predicted values and our residual values. The predicted values take the body temperature and they predict the heart rate based on the body temperature and the formula we've just created. And if we look at this, the actual body temperature of this person is 35.7. Their heart rate is 70. Our formula, based on that temperature, predicted that their heart rate would be 69. Not too bad, but it's off by a bit. And in fact, we know it's off by exactly 1 because that's the residual. The residual is the error that our formula, the difference between the actual value and what our formula predicts. Now, we would like to see these errors to be normally distributed. We don't want to see the errors at the low end always be high and errors at the high end always be low, because that would suggest there's something weird going on with the data, right? We're going on with the formula. These represent standardized values for the errors, for the predicted value and the errors. In other words, where they are in terms of z-scores for their own for the distribution weights of heart rates and body temperatures. Okay, so let's take a look at this now. So we have a formula that we can use this way and we can use predictively also. So for instance, if I wanted to predict the body temperature, what's a normal body? What's 98.6 in centigrade? Anybody know? What is 98.6 in centigrade? I'm sorry, what's that? 37.6? How do you know that? You know that because you've done clinical work outside the United States, or? Oh, okay, good. I forget. All right, so the heart rate, based on this formula, for someone whose body temperature is 37.6, is equal to negative 88 plus 4.4 times this body temperature, 37.6. Let's see what that calculates out to. The y-intercept, the place where it crosses, the place where x is equal to 0. In other words, where it crosses the y-intercept, where it crosses the y-axis. I lost track here. 4.4 times 37.6 is equal to this, minus 88. Okay, so that would predict that that person has a heart rate of 77.4. A little bit high, right? Who knows? I don't know where this data came from, if it was resting heart rates or something like that. But we could use it predictively. Is it a good prediction? Apparently not, because only 6% of the variability in heart rate was predicted by body temperature. Many, many other factors that we've missed. Well, how can we make this a better predictor? One of the ways that we can make this a better predictor is to think about what those other factors might be. BMI, level of fitness, for instance. Maybe there's a numerical value for that. You could come up with age, for instance, so on and so forth. Many other variables, a lot of them numerical variables also, that, gee, you know, if only we could consider them at the same time, perhaps adding them together, taking this additively and looking at all these factors together can give us a much better predictor than just looking at body temperature alone, looking at BMI alone, looking at age alone, and so trying to predict what heart rate would be. So it would be nice to get these other variables incorporated into this. And that's what multiple linear regression basically allows us to do, is to get other variables involved. I don't have other data for this particular data set, but we have I have a couple other data sets that we put online. One of them is exam revision. Is that what the name of that is? Okay. Let's take a look at what this data set has in it. Okay, so let's take a look at these variables. They're all numerical variables. Okay, and let's see what the labels tell us. The top line is a person's score on an exam. Second line is the hours he spent revising the exam. Third one is his level of anxiety, however that was measured numerically. Okay, and the third one is A-level entry points. I'm not even sure what that is. Let's see what that is. Okay, I'm going to assume that's like maybe his grade point average or something like that. Well, it doesn't look like a grade point average, but let's assume that it's some measure of his ability or something like that. Okay, so let's say that we want to create a formula. We want to find a way of predicting how well a student will perform on a test, given the amount of hours he puts into studying, the amount of his anxiety level for taking tests, and some other score that's based on his academic background or something like that. We want to see if we can't predict how well he's going to do on that test. Okay? That might be important, right? This might be a GRE. Might want to evaluate which students need more preparation for a GRE, for instance. So maybe we'll use that. Maybe we're using that to predict his performance on GREs and decide whether or not he should take a class or something like that. Okay, or how many hours of classes he should take. Okay, so let's look at these. Which of these is the predicted variable? Which of these are the predictors? Well, the score on the test is the predicted variable or dependent variable. And we want to use these independent variables, hours of study, anxiety level, and academic level, to predict what his score is going to be on this test. Okay, well, gee, this is going to be this interesting. Let's see if there's correlations involved here and how strong these correlations are. How did we do that before? First thing we did was we look at scatterplots. Okay, well, you want to know something? Now I'm going to have to do a scatterplot for, let's see, score and hours and anxiety, and it's going to have a bunch of scatterplots. Well, why don't we just do, let's just select a matrix scatter and tell it that we want to compare all of these variables for correlations. Let's see how that works. Okay, let's see what we have here. So these boxes are empty in the center here. Why are they empty? Because they're actually comparing the same things. Exam score versus exam score, that's going to be a perfect straight line, right? We don't have to have those boxes. However, if we look at, let's see, if we look at exam score and how well it correlates with hours spent revising, or I don't know what that means, but say studying, it's a very strong positive correlation. Well, how about anxiety level, right? Well, you know, it looks like it's not as tight, but it looks like there's a negative correlation with anxiety level. Kind of makes sense, right? And what about this last one, academic achievement, let's say, A-level entry point? Well, that seems to have a positive correlation also, right? So that's interesting, right? So let's see. Maybe we can combine these three predictor variables and get a better result in terms of our prediction of what the value would be for the exam scores. Before we go there, let's take a look at something else. Let's take a look at the hours spent revising versus the anxiety level and the academic level. You know, it looks like, as far as anxiety, it doesn't look like there's much of a correlation. You know, but there does seem to be a little bit of a correlation with academic achievement here. Okay, what about, let's see, how about anxiety and hours spent revising? No. How about anxiety and academic achievement? No. It looks like there's just this one comparison here among the predictor values that we have a situation where hours spent revising and A-level entry points, they seem to have a high level of correlation. Anybody remember what the problem was there? That's called collinearity, right? The problem is that if they're very closely associated, we don't need both of them. In fact, using both of them may throw off the influence that other factors have on here. It may impair the ability of our formula to predict the value, the dependent variable, right? So we don't like that. However, what we don't know yet is how strong this correlation is. You remember what Levi said was too strong a correlation? It's pretty high. It's 0.9, I think it's called. 0.9, right? That's a very high level of correlation, right? Doesn't look like to me that that's going to be a problem, but we can actually analyze that if we want. Let's give it a try. Analyze. Correlation. Let's just look at bivariate because I only want to know about hours revising and A-level entry point. So what we get there. Okay, now our value is 0.73. Not ideal, but not over 0.9. Right, so I'm okay with that. We're going to keep that variable in. Okay, what's the other problem that I have here on this data set? Yep. What's the other problem I have on this data set? How many variables I have there? How many cases do I have? 20. Not so good, right? Right, so we really don't have enough cases here to really do a really effective multiple regression. We're certainly not going to use the R-square value. We're going to use adjusted R-square, right? That's one of the reasons why we would use adjusted R-square is because we're dealing with a relatively small sample size and some collinearity also. Okay, so let's take a look at how we would do this. Analyze. I'm going to go to regression linear. It's still a linear regression. We're still dealing with working with a linear, a relationship that's linear in the end. Okay, so our dependent variable is going to be the exam score. Our independent variables are going to be hours spent, anxiety level, and A-level entry point. Now, how are we going to do this? There is another thing here. It says method. There's several different ways to analyze this information, stepwise, or stepping forward, stepping backwards through this data, and so on and so forth. But we're not going to do that. We're going to analyze all of these variables together at the same time. So we're going to leave this at enter. So I'm going to click OK. And I'm going to take our first shot at this and take a look at our output. Okay, and see what we wind up with. Well, overall, is our correlation, is our regression statistically significant? And what do we have for our significant for an analysis of variance? It is statistically significant, right? We can say that there is an association between the score and the exam scores and our predictor variables. Okay, so let's take a look at how strong an association that is. Well, the R value overall for all of these together is equal to 0.927. The R square value is 0.86. So the formula that we're about to create accounts for 86% of the variability in the response variable, the dependent variable. That's really good, right? That's excellent. Yes? That's a good point. We're going to use the adjusted one instead. The adjusted one is going to be higher or lower? always going to be lower, right? So we're going to use, in this case, we're gonna use the lower one instead. We're going to say that our adjusted R-squared value is still 83%, right? So there is still some variability here, but we really accounted for a lot of this variability. So let's take a look at this. These are our coefficients. So how is this formula structured? Well, now we still have a y-intercept, right? It's still a straight line. So our y-intercept, our formula now is going to be y is equal to a plus b1x, b1x1 plus b2 x2, not squared x2, plus b3 x3. What's that going to be? Well, that's equal to the exam score is equal to the y-intercept, which was negative 12, I'm going to call it, plus hours spent, 0.55 times hours, plus 0.1 times, I'm rounding these off, times anxiety. Was that negative or positive? Was that negative? Is that positive? That's positive also. Okay. You get some strange effects when you do multiple regressions sometimes, because it's influenced by that collinearity. It's influenced by other things you're doing. Okay, and plus 2 times the A level. Okay, so that is our regression equation. Well, what does that tell us? That tells us that for every 10 hours that this person revises or studies, his score is likely to go up 5.5 points. For every value of anxiety that he goes up, that his score will go up small amounts. Kind of an odd result, but it may be because that's influenced by the hours and the A levels, correcting for the hours and the A level. The A level, again, for whatever that represents, whatever that score represents, for every value it goes up, every value goes up 1, it's multiplied by 2, and that raises his exam score. So that is an equation that represents the relationship between the dependent variable and these 3 independent variables. What would this have looked like in terms of regression, or if we had done each one of these individually without doing a multiple regression? Okay, let's take a look at this. Let's take a look at just hours spent. Okay, in that case, the R value is 0.82, right? It suggests a lot of the variability, but not all of the variability. And R squared is equal to 0.67. It's only 67% of the variability is predicted if we only use that one variable. The other one that was pretty strong association was the A level. Let's see. Let's see what A level does for us. Okay, what is R squared if we only considered that? Was 0.76. So combining these gave us a better predictor. Formula was a better predictor than the individual independent variables analyzed separately. Okay, any questions on that so far? You guys okay with that? Okay, so let me see what else I can do with this. There is something else I want to point out in this table. This particular table doesn't have it though, so I gotta go a little bit further. Regression linear. Move these back in. values and anxiety, statistics, intervals, descriptors. Let me see if I can find what I'm looking for here. I think so. Yes. From the ANOVA table, yeah. Well, and you also see individual significances for each of the variables. The overall significance you get from the ANOVA table. Okay, here we go. Let's see. Okay, so one of the things we're interested in when we do regression is we're interested in understanding how much of an influence a predictive variable has on the outcome. So let's say we're public health people and we have $1 million to invest in a public health program. Some of it might be education, some of it might be outreach, some of it might go into other things. We want to know what's going to have the biggest impact in terms of public health. So what we can do with regression is we can observe that this variable, if we increase this particular variable, what kind of impact it's going to have on the outcome. And if we increase heart rate, what outcome it's going to have, body temperature, what outcome it's going to have on the heart rate. If we increase funding for educational programs, what the result of that's going to be for rates of diabetes, for heart disease, and so on and so forth, right? So this idea that these equations can help us focus on which of these variables has the biggest impact is important. So we did that. We started to do that by looking at the values themselves. So for instance, for every hour that they spent studying or revising, it increased the score on the test by a half a point, right? Now, on the other hand, for whatever A-level entry was, that actually, for every increase of 1 in that scale, we got an increase of a score of 2. Looks like that had more of an influence. The only problem is that these are two completely different scales, right? So it's like comparing apples and oranges, you know, in terms of what their influence is. So what we need to do is we have to look at these values that we have for A-level entry points and for hours spent, and we have to standardize those numbers that are in our data set. And we have to look at, well, how much of an influence going up 1 standard deviation does this have, not increasing it by just a certain number. So the problem here is that they're different scales. This standardized coefficient, this gives us a window onto which of these variables has the biggest impact in terms of the range of numbers that it really occupies. Like age is different than blood pressure and so on and so forth in terms of the range of numbers. So it looks like A-level entry point has the biggest, this is standardized for that scale. So these, you can compare these are apples and apples, where these are apples and oranges. So these are a little bit better way of predicting which of these has the biggest impact, changes in which of them has the biggest impact. So it looks like A-level entry point has the biggest impact, closely followed by hours spent at revising, and anxiety didn't have as strong as an impact on that. Now, anxiety was a completely different scale, so it was hard to compare these coefficients, unstandardized coefficients, to each other, but these standardized coefficients are a little bit easier to understand how the same kind of movement in each of these scales impacts the final result. Okay, so we're looking for whatever gives us the biggest result here, or looking at them comparatively. Okay, so tell you what, there's another one. You guys have computers and you're sitting there in front of the computers. Let's do another one, except you guys do this one. We have another data set there that's called child data. It's on this week's, it's on the multiple regression. Yeah, it's under the weekly materials. And let me see what it's got in it. It has, the variables are age, memory span, IQ, and reading ability. So I'm thinking the IQ, short-term memory span, age. I'm thinking that we want to predict the reading ability based on age, short-term memory span, and IQ. Right? That sounds like the right direction. I don't see it going either way. So first thing, do a matrix, do a scatterplot matrix to see if there seems to be positive correlation between reading ability and each one of these various other predictor variables, age, short-term memory, and IQ. And then look at age, short-term memory, and IQ to see if there's collinearity between any of those. If there's too strong an association between them, which would suggest you only really need one of them. Let me see how things are going online. How are you guys online? Have I put you to sleep yet? Apparently, yes. That seems to be the case. Go Scatterplot, legacy dialog, Scatterplot. You don't have to use legacy dialog if you don't want to, if you've been using something else. You can use whatever you feel comfortable with. But legacy, Scatterplot, and then matrix. Matrix Scatterplot. And then move all of them over. It'll give you a 4x4 set of graphs. Now, Levi did a version of it using R that gave him the same thing, except it also put the R values in, in every other box. I can't see that. I'm going to do it up here. I'll do it up here so you can see it. See if you got the same. If you got the same thing as I got. Let me get to it though. Oops, one. Oh, I meant to, yeah, I did. I got ahead of myself there. I forgot what I was doing. Okay, so our dependent variable is reading ability. It's the bottom, where I put it, it's the bottom. Maybe different on yours, but where I put it, it's on the bottom row, right? So if I go across here, it shows me the scatter plot for reading ability versus age, reading ability versus short-term memory span, reading ability versus IQ. So I can visually look at these and say to myself, does it look like there's an association? Well, yeah, kind of, not so sure, but kind of, right? Okay, now on the other hand, if I'm looking for collinearity, IQ, where it can be, so I'm not worried about that. I'm worried about if there's an association between IQ and the other predictive variables. Not very strong, no problem. I don't think it's going to be a problem with collinearity. Better to calculate the R value, but you can see right here, it's not going to be 0.9. Okay? And how about short-term memory span and age and IQ? Also, not that strong in association. So it doesn't look like we have collinearity issues here. And again, collinearity at the extreme might be if you try to use BMI and height and weight as 3 predictor values. BMI is already a combination of height and weight, right? So you're not getting any more information by putting in height and weight as predictor values, right? But that's an extreme case. That would be an R of 1, for each one of them. Okay, I got nobody online to respond in the chat box. You guys are there, right? Okay, good. Glad to hear it. Any questions online? You can type into there. I'm going to go on and go to the next part of this. Okay, so now let's skip past correlation and let's create a regression formula for this. Okay, so go to Analyze. Yeah, Regression Linear. And go ahead and decide which is the dependent variable and which are the independent variables. Yeah, right. Right, that's what we're trying to predict. Right, and IQ, short-term memory, and the child's age. Those are all things that might contribute to that. Now, reading ability is not going to affect the child's age. Obviously, won't go the other direction. Okay. I'll give you guys another minute or two. I'm going to go ahead with this. Okay, let's look what I get. Okay, so first of all, starters. What is my, is there an association, where am I? Am I at the bottom? Yes, I am. Okay, so another very strong correlation, right? Is this statistically significant? Yes, it's statistically significant. This equation, we don't know yet if it could be statistically significant and have an R value of 0.1, right? Not be very important clinically or practically. But in this case, it's statistically significant, but it also has a very high R value, R squared value. In this case, am I going to use adjusted R squared? Do I have good reasons to do that? Yes, small sample size, right? A little bit of collinearity, some small sample size. We didn't check to see how normally distributed these predictor variables are and so on and so forth. So it seems sensible to use the adjusted R squared, which suggests 80%. These are ridiculously good. You'll never find this good, really. Yeah, 80% of the reading, 80% of the variability in the reading level can be predicted by these three values, right? And we can create a formula now. And that formula is going to be the reading level is equal to negative 0.106 plus 0.466 times the child's age plus 0.269 times the child's short-term memory plus 0.025 times the child's IQ. Okay, and are all of these statistically significant themselves? Doesn't look like it, right? We've got a little bit of issue with short-term memory. So that's a little iffy. Overall, statistically significant. That seems a little worrisome. Okay, so we take that formula, we can actually calculate what the actual predicted values are and compare them to, yes?
Short-term doesn't include the longer that much. You take it out, it's just about.
Oh, okay, so we could get rid of short-term memory. I wonder if, yeah, and it's not statistically significant. Did you run the correlation between short-term memory and the others? 0.7? Yeah, so yeah, it could be a little bit of collinearity or small sample size, also not very significant, so it could be a combination of those things. So yeah, that you found a situation where it really doesn't help us, so why keep it in there if it's not improving our predictive value? So at any rate, so we created this formula. Again, we can find our predicted values, our residuals. We want our residuals to be, our errors, our residuals to be normally distributed. We don't want them, all on one side of the line, all on the other side of the line, and so on. And so or very widely distributed at the low end and very tight at the high end. So we don't want to see any of that kind of stuff in there. We want everything to be normally distributed. So in essence, you can use this to analyze associations between numerical variables. I'm going to take a quick look at this stage. We got about 10 minutes. I just want to, at this stage, let's talk about how this all impacts what you guys are doing with your project. And I'm going to open up at least one of the data files that you have online. Let me get things out of the way here. I know I got them here somewhere. Here we go. Let's see. Temperature rate. Nope. That's just in here. Simple linear regression. No, it's not in there. Oh, let me do it this way. Community Health Survey. Let's open up this one. The flu set. Okay, so what we've done here is we've given you two separate data sets. One of them is the full Community Health Survey data set. Let me open that one too at the same time. This one's 2014. I think you have 2013. But basically same kind of thing. And where the variables that we've given you, there are 10 of them for the reduced data set. Right? So if you're not going to be too adventurous, you can work with a data set that has only 10 variables. Okay, but what are those variables? We have a person's age. There happens to be a numerical variable there, right? As in one of the few that are in this data set. It has their borough of residence, right? The borough that they live in. Has their race or ethnicity. Right now, you'll notice it's not coded. I don't know if your copy is coded or not. If it isn't coded, what are you going to do to find out which borough, what one represents what two? You got to go to the code book, right? So you can find the code book. Here's a 2014 code book. Again, it's a little bit different than yours. So, for instance, for new race, that variable called new race. Okay, what does that stand for, new race? Well, 1 is white non-Hispanic, 2 is black non-Hispanic, 3 is Hispanic, 4 is Asian Pacific Islander, 5 is other, and so on and so forth. You have to go in there and code it if you want to be able to get decent graphs and charts out of it. But let's get past that now. Let's just go take a look at the actual data itself. This is let's see, new race. That's a categorical variable. Borough, 1 through 5, categorical variable. Insured, 1s and 2s. I'm guessing that's a categorical variable, yes or no. Type of insurance, insured 5 might be kind of insurance. You know, instead of 2 values, yes or no, now you have the type of insurance: Medicare, Medicaid, private insurance, Obamacare, whatever, right? You'd have to look up in the code book. There was no Obamacare invented. Yeah, there was, but no. 2009, yeah, 2014, yeah, there's Obamacare. Yes, am I wrong? Yeah, 2000. They passed it in 2009. Then 2 years later, there was a Republican Congress. Both houses were Republican, so forget it. There was nothing else. They were trying to repeal it the whole rest of the next 6 years. So yeah, it was around 2014, about 2013, but certainly 2014. Okay, flu shot, yes or no? Gender, right? So for instance, if I wanted to see if there was an association between getting a flu shot and a person's gender, both of those are dichotomous, 2 values. Yes or no, flu shot, male or female, right? So what would I use? What kind of test would I use for that? Right? Categorical, 2 values. I'd make a table, right? Chi-square table, right? Use chi-square. Since it's a 2 by 2 table, what else? What other statistics can I use? I can use odds ratio. and I can use relative risk. Okay, don't look at me like, this doesn't mean anything to you, please. You can use odds ratio. What's that? So in other words, yeah. So for instance, I could literally go in here right now, analyze descriptive statistics, crosstabs, and I could organize those values. Gender, I'll put gender into the rows. I'll put received a flu shot into here, and say, give me some statistics. Give me a chi-square. Give me risk, and say, okay. Okay, what do I get? I get my chi-square table over here, right? Where is it? There it is, right? This is a male or female. You'd have to, do your coding, and instead of 1 or 2, you get male or female. You get flu shot or no flu shot. And let's see, what percentage of people? I'm going to go back here and do it one more time. Analyze the descriptive statistics crosstabs. This time I'm going to go into the cells. I'm going to say, show me the percentages by rows. Okay, so as far as risk is concerned, 42% of people who are 1, whatever that is, male or female, got a flu shot, and 46% of people who are 2 got a flu shot. That's assuming that 1 is yes and 2 is no. I don't know if that's the case or not, right? So that's your crosstab table, right? Okay, and you get to compare the percentages. Here's your chi-square test, 12, right? What's the significance? 0.000. So there is an association between gender and whether a person gets a flu shot. Maybe males or maybe females are more, maybe females go to the doctor more often than males do. Whatever reason it might be. There is an association. One group that statistically significantly gets more likely to get a flu shot. Well, about the odds ratio. The odds ratio is for whatever this is, 1 or 2, is 0.55, right? Which means that whichever that first value is, that your 85% is likely as the other one to get the flu shot. Your odds are lower that you'll get the flu shot. So maybe that first one, maybe 1 is male, 2 is female, right? Your odds of getting a flu shot are 85% of what the odds would be for a female. You have lower odds. Right? If that were 2, it would mean you're twice as likely. Your odds are twice as high that you would get a flu shot versus the other group. And then again, it's hard for me to really say what this really says because I don't know I haven't looked up what 1 and 2 stand for, right? And your odds ratio. And the next one is your relative risk. Same kind of measure. How do I know they're statistically significant? Because it would normally, the null hypothesis says that the odds ratio is 1. The odds are the same for males, same for females. So the odds ratio is equal to 1. If that's your R, and your odds ratio R is equal to 1 is your null hypothesis. Not equal to 1 is your alternative hypothesis. How do I know it's not equal to 1? The 95% confidence interval for the odds ratio and relative risk don't include 1. Okay. So this is the way we would use this. If I was looking at different variables, if I was looking at age, if I was just predicting whether or not, what's the average age of people who got a flu shot versus the average age of people who didn't get a flu shot, I would go over to flu shot, right? Flu shot yes, flu shot no, 2 values, right? 2 categorical values. The age is a numerical variable. So I could calculate the average for males and for females, the average age for males and females. What test do you use to compare the average of 2 groups? Use a t-test, right? What if I wanted to compare the average age for the average age of people in the different boroughs? How many boroughs are there? 5. Your categorical variable has 5 values. If I was looking for the average and compare the average age of people in the 5 boroughs, I'd have to compare 5 averages. Too many for the t-test. I'd have to use the analysis of variance because that allows me to compare the average for more than 2 groups. Right? So you use analysis of variance there. How about if I had another numerical variable, for instance, where I had age, which is the first column, and I had BMI as another value. 2 numerical variables, right? How do I look for an association between 2 numerical variables? Correlation and regression, right? Which is just what we were doing here. Correlate. The numerical implies causation. In other words, one of those, age or BMI, would have a predictor value for the other one. So if you're just looking for an association, you stop at correlation, right? But if you're trying to show that one can predict the other, then you use regression. And really, that's really what you're asked after most of the time. You want to use this as a predictor. Okay, so now this is only a small data set, right? You have 200 different variables that are in here. A lot of them, most of them are admittedly are categorical. So a lot of people are going to have to work with chi-square and so on and so forth. If they're lucky, they'll be 2 by 2. Well, no, analysis of variance is for numerical, right? You're comparing means. So if you're working only with categorical variables, there's no average. Right? There's not an average, male or female. It's not an average male or female, right? So those are categorical. So you almost always be working with tables, chi-square. If you're lucky and you have a 2 by 2 table, you might be able to use odds ratio also, right? So, but there's a lot of categorical data in here. There's data about smoking. There's data about asthma. There's data about, so you don't have to limit yourself to just this flu stuff. Go run through them, find things that you're interested in. Gee, I'm kind of interested in if there's an association between someone being diagnosed with asthma and also having a mood disorder or something like that, which is another one. There's about 10 different variables that measure mood or something like that, that predict with self-assessment or the other ways of predicting mood, depression, mood. In other words, maybe, have you been diagnosed with asthma in the past 12 months, right? And have you been diagnosed with depression in the past 12 months? Is there an association there or not? Be interested. I don't know. I don't know if the data is there either. I'm just saying that it may possibly be there. Right? Certainly the data is there for, have you ever been told you've had asthma? And have you experienced depression in the last 12 months? Right? Certainly that data is there. So you can look, see if there's an association. So I'm encouraging you to take a close look at this and come up with something interesting. You don't have to use the ones that we're throwing at you. You have a lot of information in that community health survey that you can pick out something you're interested in and make it a little bit more interesting for you to research it. Now, what are you going to do when you do this? Well, first of all, number one of the things you might be interested in doing is telling us about the population. Who are these people? What's the average age? What's the age distribution, right? There's nobody under 18, right? You might want to make a histogram of the age distribution. How many of them are males and females, right? You might want to make a bar chart, males and females, or pie chart, males and females. How many of them, think about what might be relevant to, if you're looking at mood and asthma, okay, you're going to do that, but you want to give us some descriptive statistics, some background. What percentage of people in this population experience mood disorders? What percentage of people in this population have been told they have asthma? Just for starters, even before you actually go in and do the analysis. So you want to give us an objective. You want to tell us what you're doing, what your objective is. You want to give us some descriptive statistics. Charts are great there because charts give you a better handle on presenting data without making people read a lot of words. You can see you get it right away. Then you want to research it a little bit, give us some background on asthma and mood disorders. You might want to tell us what statistical analysis you applied. Then give us the results, and then give us your conclusions. Okay, so you kind of got, I think, at this stage, I think you're starting to wrap your heads around what we need to do. Okay, let's call it a night. Right? I think we're about done. I see I got some questions online. I woke them up. Okay. What is a good follow-up test to a chi-square that shows there is a significant difference among categorical? Is there anything you can do to talk specifically about that? One of the things that you can do, this is a little bit adventurous, is that if you have a chi-square table, like ethnicity and disease or something like that, it's 5 groups, you might want to divide that up and examine groups separately. In other words, make a new variable that has, for instance, one ethnic group and then the rest of the population, a second ethnic group and the rest of the population. So it gives you a 2x2 table instead of a 5x2 table. Because then you can say, well, the odds ratio for Hispanics compared to all other groups is 2.3. The odds ratio for blacks compared to all other groups is that you can restructure the data using that transform, create a new variable, and then move over, Hispanic is, say Hispanic is 1, make 1 in the new variable, it's still Hispanic, but then make 2 everybody else, all of the blacks, all of the whites, all of the non, so on and so forth. And so you can create that. Okay, I'm going to do a review session on Thursday for the BIOS 610 class, and some of them are going to be doing a project also. If you post questions or issues you have with the data, or doing something like that, manipulating the data, put it on Blackboard in the discussions forum.